Welcome to the final topic of this first module of the Environmental Biotechnology course. In this lecture, we'll focus on biomass retention. By the end of this lecture, you'll understand why it's a cornerstone of environmental biotechnology and how it shapes wastewater treatment processes. So what exactly is biomass retention? In biotechnological processes, we deal with two critical timelines. The hydraulic retention time, this is how long water stays in the reactor, and the solid retention time, this is how long the solids, or biomass or bacteria, remain in the reactor. In systems without biomass retention, like most industrial fermentations, the solid retention time equals the hydraulic retention time. This means bacteria must grow fast enough to keep up with the water flow leaving the reactor. Otherwise, they are washed out. In environmental biotechnology, we use biomass retention to separate the biomass from the water as it leaves the reactor. The biomass stays behind, allowing us to extend the solid retention time far beyond the hydraulic retention time. Why does this matter? It gives us control over bacterial growth rates, independent of how fast the water flows through the system. The excess biomass is still produced and removed, but retained biomass boosts the system's efficiency. Why is biomass retention so critical in environmental biotechnology? It's all about dealing with dilute systems. Natural water contains 0 to 0.2 gram per liter of organic carbon. Municipal wastewater is of course a little bit more concentrated, but still has only half a gram per liter of organic carbon. Industrial fermentations, however, are fed with up to 100 gram per liter of organic carbon. Now, the amount of biomass that can grow depends directly on the available carbon. In industrial fermentation, you might produce 50 gram per liter of biomass. But in wastewater, this would only be 0.1 or 0.2 gram per liter of biomass. Low biomass means low volumetric conversion capacity, the amount of substrate you can process per cubic meter of reactor per day. By retaining biomass, we increase the concentration in the reactor, boosting the volumetric conversion capacity. This allows us to build smaller, more economical reactors. Let's look at real-world comparison. The simplest form of wastewater treatment is the lagoon or oxidation pond, often used in more rural areas. These are large artificial lakes with some aeration but no biomass retention. The bacteria grow only as fast as the wastewater allows, limiting treatment efficiency. Now compare that to systems with biomass retention like trickling filters or activated sludge processes, which are common in traditional wastewater treatment plants. These systems dramatically increase the volumetric capacity, meaning smaller equipment and lower cost. As you can see in the table on this slide, biomass retention makes treatment systems more compact and efficient than, for instance, in lagoons. The simplest way to achieve biomass retention is through biofilms. Biofilms are slimy layers of bacteria that naturally form on surfaces, like the plaque on your teeth. In a reactor, bacteria colonize surfaces, immobilizing themselves and forming a biofilm, while the wastewater flows over the biofilm surface. One of the oldest and simple biofilm systems is the trickling filter. Here wastewater is sprayed over a solid medium like rocks or modern plastic media, when bacteria grow as a biofilm. This setup allows high biomass concentrations, but its capacity is finally limited by the biofilm surface area. Trickling filters provide 50 to 200 square meters of surface area per cubic meter of reactor. As a rule of thumb, each square meter of biofilm can transfer around 10 grams of oxygen per day. This translates to a volumetric capacity of 0.5 to 2 kilograms of oxygen per cubic meter per day. The challenge would be to increase the specific biofilm surface area to optimize the process. While trickling filters are still used with modern media, the activated sludge process dominates wastewater treatment nowadays. Developed over a century ago, this process mixes wastewater and bacteria in an aerated tank. Instead of growing on the surface, bacteria form flocks, clumps of biomass that can be settled out by gravity after the treatment. This settling process effectively limits the treatment capacity. Flocks settle slowly at about 1 meter per hour, require large so-called clarifiers to separate the biomass from the treated water. Also, the settled biomass has a low concentration, limiting the concentration in the aeration tank. In this wastewater treatment plant, the smaller central tanks are, are where the treatment happens, while the larger circular tanks with bridges are clarifiers for biomass separation. These clarifiers take up a lot of space, but the system is still much more compact than lagoons, achieving biomass concentrations of up to 4 gram per liter and volumetric capacities of 1 to 3 kg oxygen per cubic meter per day. The limitation here is that clarifiers can't handle biomass concentrations above around 4 gram per liter, or the settling process will fail. To wrap up, biomass retention is important in environmental biotechnology. By keeping bacteria in the reactor longer, we boost efficiency, reduce reactor size, and make wastewater treatment more cost effective. Whether through biofilms and trickling filters or flocks in activated sludge systems, biomass retention is what makes modern wastewater treatment possible.